My name is Zulfikar. In this video, I present my Emertxe internship project, which is a real-time electric vehicle dashboard and ADAS warning system. The project uses an STM32 Blue Pill microcontroller, Pixem Lab simulation, UART communication, and a Python dashboard. I will first explain the project using the presentation, then I will show the code structure, and finally I will demonstrate the working simulator and dashboard. This presentation is divided into four parts. First, I will explain the project idea and objectives. Then I will describe the system architecture and STM32 peripherals. After that, I will show the firmware models and UART data format. Finally, I will move to the code walkthrough and live simulation with the dashboard. For the project motivation, in an electric vehicle, the dashboard needs to monitor important values continuously, such as speed, battery, SOC, motor temperature, accelerator input, braking input, and remaining range. At the same time, safety systems are important because the vehicle should detect front collision risk and blind spots. This project combines EV monitoring and ADAS features into one embedded system. The objective is to build a complete simulated embedded system. The, the STM32 reads analog and ultrasonic sensors input, processes the EV behavior, detects ADAS warnings, manages faults, and sends real-time telemetry to an external Python dashboard. The system starts with Pixem Lab sensors. Four potentiometers represents accelerator, brake, battery SOC, and motor temperature. Three ultrasonic sensors represent the front, left, and right distance. The STM32 reads these values, updates EV and ADAS logic, checks faults, and sends UART frames to the Python dashboard. The main development tool is STM32 Cube IDE, which is used to configure and program the STM32 we are using. Pixem Lab is used to simulate the blue pill board and sensors. Com0com creates the virtual serial connection between the simulator and Python. Python uses PySerial and Matplotlib to build the dashboard. Now for simulation inputs and pin mapping, the ADAS inputs are PA0, PA1, PA2, and PA3. PA0 is the acceleration, PA1 is the brake, PA2 is the battery SOC, and PA3 is the motor temperature. The ultrasonic sensors uses GPIO trigger and echo pins. The front sensor uses PB0 and PB1. The left sensor uses PB2 and PB3, and the right sensor uses PB4 and the PB5. USART1 is used for telemetry with PA9 and transmit and PA10 as receive. The STM32 project used several peripherals. ADC1 reads the analog inputs. GPIO controls the ultrasonic trigger and echo pins. Timers are used for periodic scheduling and microsecond timing for the ultrasonic sensor. USART1 sends the telemetry to the PC dashboard. The firmware is divided into modules. Main.c controls the application sequence. EV control.c handles vehicle behavior. Ultrasonic.c handles distance measurement. ADAS.c makes the warning decisions. Full.c manages fault flags. UART shell.c handles UART comments and telemetry output. This modular structure makes the project easier to debug and explain. The EV model calculates torque and speed when the accelerator is high, brake is low, and no fault is active. Torque become positive and speed increase. When brake is applied, torque is reduced and become negative. If a fault is active, the fault manager can force the torque to zero so the speed remains safe. For ADAS warning system warning logic, the ADAS model has two main functions. Front collision warning uses distance and time to collision if the object is close. The system raises a warning if it is critical. It sets a critical alarm and collision fault. Blind spot detection checks the left and the right distances when the vehicle is moving above the threshold. The fault manager monitors critical conditions. Fault 0x01 represents motor over temperature. Fault 0x02 represents low battery SOC. Fault 0x04 represents critical collision. These values are transmitted to the dashboard and also explain why the vehicle may stop or prevent torque output. UART is used to send real-time data from the STM32 to the PC. The first line contains EV values such as speed, SOC, torque, temperature, range, accelerator, and brake. The second line contains ADAS values such as front distance, left distance, right distance, time to collision, collision level, blind spots, uh, alarm level, and fault code. The Python dashboard reads this format and extracts the value from it. The Python dashboard reads UART data through COM11 and visualizes it. It showed the speed, gauge, battery percentage, torque, accelerator, brake, motor, temperature, alarm status, fault code, and ADAS bird eye view. This makes the embedded data easier to explain during the final demo. The main challenges were configuring peripherals correctly, scaling the inputs, integrating all modules, and making UART communication stable. The simulator's serial connection required careful setup using COM10 and COM11 at 9600 baud. I also had to avoid using multiple serial methods at the same time because that caused conflicts. The stable setup is Pixum Lab serial on COM10 and Python dashboard on COM11. Next, I will briefly show the code in STM32Cube IDE. I will start with main.c and the application loop. Then I will show the EV control module, ultrasonic module, ADS module, fault manager, and UART shell. I will not explain every line. I will focus on the role of each model. In the live demo, I will first show the normal safe condition. Then I will increase the accelerator to show the speed and torque behavior. After that, I will apply the brake, simulate low SOC, simulate motor over temperature, reduce the front distance for collision warning, and reduce side distances for blind spot detection. Finally, this project demonstrates a complete embedded system workflow. The STM32 reads simulated EV and ADAS sensors, process vehicle logic, detects warnings and faults, and sends telemetry to a Python dashboard through UART. Through this project, I practiced STM32 peripherals configuration, ADC, GPIO, timers, UART communication, modular C programming, simulation, and debugging. Now, for the project structure, the project is divided into organized folders, which is inside core SRC and INC. So the project is divided into these separated models instead of writing everything in main.c to make it organized. So if we expand INC, we will see EV control dot I meant SRC. We will find EV control dot C, ADAS dot C, fold.c, ultrasonic.c, UART shell.c, and main.c. Each model has a specific responsibility which make the project easier to debug and explain. So going to main.c, uh, I included the project models and create the main handles of EV control ADAS and fault handling. Now in the initialization, the firmware initialized the EV models, ADAS model, fault manager, ultrasonic driver, EWM, timers, and UART shell. And then going to the main loop. In the main loop, uh, the firmware first checks if any UART command was received. Then it processes shell commands. After that, every 100 milliseconds, the system reads sensors and updates the logic. Uh, Additional to that, the sequence is important. First, ADAC values are read. Then EV model is updated. Then ultrasonic distances are read. After that, the ADAS logic is updated. Faults are checked, and the status is printed through UART. This printed status is the same data used by the Python dashboard. Now, going to the evcontrol.c, this file contains the EV model. It reads the accelerator, brake, SOC, and temperature values. Then it calculates torque and speed. When the accelerator is high and brake is low, torque become positive. When the brake is high, torque is reduced. If a fault is active, the torque can be forced to zero for safety. Now going for the ultrasonic.c file. Uh, This module controls the HC-SR04 ultrasonic sensor. It senses and the trigger pulse, waits for the echo signal, measures the echo time, and converts it into distance. The measured distance are later used by the ADAS module. Now, for the ADAS.c file, we will talk about uh, that this file contains the ADAS decision logic. It checks for the distance and time to collision for collision warning. It also checks the left and the right distances for blind spot detection. Based on these values, it sets collision level, blind spot status, and alarm priority. Now going to fault.c, this is the fault manager. It checks the low SOC, motor over temperature, and critical collision. Each condition activates a fault flag. For example, 0x01 is temperature fault, 0x02 is the low SOC, and 0x04 the collision fault. For the UART.shell.c, we have this file handles UART communication. It sends the startup message, receives commands, and prints system status. The dashboard depends on this UART format, so the output must remain consistent. Now I will move to the live simulation and dashboard. So basically, for the left part of the screen, it shows the spare parts. This is the Pixel Lab simulation layout. The four potentiometers represent the analog EV inputs. PA0 is accelerator, PA1 is brake, PA2 is SOC, and PA3 is the motor temperature. Now for the ultrasonic sensor, these three ultrasonic sensors represent the front, left, and right distances. The front sensor is used for collision warning. The left and right sensors are used for blind spot detection. The Python dashboard receives the UART telemetry from Pixem Lab through COM11 and display the data visuality. Uh, so here basically I start the simulation with a normal safe condition. The accelerator is low, the brake is low, the battery SOC is safe, the temperature is safe, and all distances are far. The dashboard shows no alarm, no active fault, and signal is on. This means the UART connection is working and the system is receiving live telemetry. So now I will increase the accelerator input, the STM32 PA0 potentiometer. Since the brake is low and no fault is active, the EV control generates a positive torque and speed starts increasing. And this is what we will see. So here I increased the PA0 and the speed was 30. Wait until the update. Okay, it increased to 31. And the torque became positive, as we can see here. The speed is increasing for positive acceleration. Uh, so for now, we are checking or simulating the brake test by decreasing A0 and increasing A1, PA1. We will see that the velocity is decreasing continuously. Now we are going to check the low SOC fault. So by decreasing PA2, which is for the SOC charge, we will see the change in the battery, the big decrease in the battery, and that was very normal. Now if we decrease it more and more till zero, the battery percentage will go to zero, and that's what we are seeing right now. And the alarm will check by red, and the fault will give us 0x02. Now when we increase it again, the the alarm will will go, and the fault will go like that, exactly like that. Now we are going to test the temperature fault by increasing the temperature PA3 level. We will see that the fault gave 0x01. That's corresponding to the temperature fault. Now, uh, get the take of the fault by decreasing again the temperature. The fault gone. Now we will test the potentiometers or the ultrasonic sensors, and especially the front distance. And when we decrease the value, we saw that the alarm gave the critical and fall 0x04 because the front the car is very close to our car. And the same thing uh, Also will be for the left and the right ultrasonic sensors. To conclude, this project demonstrates a complete embedded system workflow. The STM32 reads simulated EV and ADAS sensors and process the vehicle logic, detects warnings and faults, and sends telemetry to a Python dashboard through UART. Through this project, I practiced STM32 peripheral configuration, ADC, GPIO, timers, UART, communication, modular C, programming simulation, and debugging. Thank you for watching, and big thanks for Emertxe for this uh, nice uh, internship they gave us. Thank you, everyone, and good luck.